introduction. I'm Joe from Fluid Numerics. We are based here in Boulder, Colorado. So we're still a day behind y'all. I'll go ahead and jump right in. There's a bit of introductory material that I did want to cover because I gathered that, my background primarily is in applied mathematics and in higher order methods, and that might not be everyone's forte. So I did want to start off by giving you guys a little bit of background of where this code has come from, and a little bit of a high level of some of the algorithms that are involved with doing spectral element methods to really just solve PDEs and in particular conservation laws. And once we get through some of that material, this kind of sets the stage to talk about the software design pattern. The big push that we've been going through for the last 2 years has really been to do a lot of restructuring to make self, particularly the library portion of the code, a bit more useful for others. So it's not geared towards just doing fluid simulations, but it can be applied to more general conservation laws. Back in 2020, I made the decision to switch away from using CUDA-Fortran and hop on over to HIP with the idea that we could start running self on different types of GPU platforms. We've been doing some experimentation with OpenCL as well, with limited success in the early 2020s, but we're looking at taking a stab at that again next year. But I did want to give you guys a comparison of how we're doing memory management now with HIPFort in comparison to CUDA-Fortran. Talk a little bit about how you implement GPU kernels in HIPFort, and again with those comparisons back to CUDA-Fortran, because there's a lot of changes that come along the way when you do that. And I'll go into detail on how we're doing the domain decomposition and how we're doing MPI plus HIPFort, and how that's all coming together. And we'll show a little bit of where we're at currently with some benchmarks that we have on systems we have available here at our office and with AMD. If we have time, I'd like to get into talking a little bit about how we're doing some of our testing. As right now, I'm a sole maintainer, sole developer of this code. I've been carrying it since 2014. And I'm pretty excited to start automating a lot of my work away so that I can actually make a bit more progress a bit more rapidly. So we'll start with that brief history, just to give you a timeline and a feel for how old this code is. It's actually not that old in comparison to a lot of Fortran codes. So back in 2014, when I was in grad school, I took a course in Spectral Element Methods from David Capriva at Florida State. And throughout this course, the idea was to get to a point where you're essentially implementing discontinuous Galerkin, continuous Galerkin spectral element methods, and going through a lot of pretty typical validation activities. And at the end of that course, I ended up leaving with a fairly complex shallow water solver in 2D and a 2D compressible Navier Stokes solver. So I was pretty excited to be able to do something within a 3-month period of a course. And I always kind of use this code as a test bed for experimenting on new and emerging hardware to understand what it takes really to jump from one platform to another. It was around that time I had taught myself how to do MPI when at the time Florida State did not really have a specific program for learning how to program MPI. It was just something you sort of picked up along the way. So this code has really been a part of a learning experience for me for these last, 7 years at this point. But yeah, in 2015, 2016, I broke apart the solver into a library portion where you can essentially define unstructured grids, where you can do various calculus operations like divergence, gradients, and curls, in complex geometries, and tried to rewrite a lot of what I had done originally in terms of, fairly, I'll say it was loose at the time, but it was starting to take form into more standardized API for building out conservation law solvers. In 2017, I started doing some work with some summer students at Los Alamos's Parallel Computing Summer Research Internship, looking at doing MPI plus code development. On one hand, we were looking at OpenACC for GPU acceleration. And on the other side, we were looking at doing MPI plus OpenMP for basically doing OpenMP for on-core or on-node parallelism, and MPI for internode communications. After doing a lot of that work, we started looking into CUDA-Fortran to really squeak out a bit more performance on the GPU side. Of course, a lot of us went through this around the same time where we jumped ship either into the OpenACC or CUDA-Fortran world if you're, a Fortran programmer. And this kind of led us to a situation where we're stuck using the one compiler from PGI, which, is, I guess it has its pros and cons, but in terms of making sure you can reach multiple, variety of users who might not have access to PGI compilers, this did start to limit who your code would be applicable to, which I was really excited to see some of the stuff that was coming out from AMD, particularly the HIP project. And in 2020, I started doing a little bit of a port from CUDA-Fortran over to HIP, which in the process, I saw I was just writing a lot of boilerplate code to provide like an ISOC binding layer to expose a lot of the HIP API into Fortran. So early 2020, we put out HIPFortran, which encapsulated, I wouldn't say all of it, but 75 to 80% of the HIP API, just enough to do mem copies and kernel launches and stuff from Fortran, just to make that easy. And we ended up working with AMD to get that brought over to HIPFort. Since that transition happened, we've been steadily working through getting the rest of self kind of updated, clean up the API a bit, and finish out that transition over to HIPFort. So these development plans I'm putting up here just to give you perspective in terms of like the scope of work that we've been working on since the beginning of 2020. And I'll be talking a little bit about this pattern-driven design at the very top here. But when we went through and kind of deconstructed self yet again, I found basically in that second rendition that we did, there was a lot of stuff that was, again, really specific to compressible fluid flow. And I wanted to go back through and make this code a little bit more applicable to general conservation laws. So there's a bit of refactoring that was done there. The MPI level parallelism I had in place before was actually fairly complicated. And we ended up having to use quite a bit of additional tooling to do domain decomposition for unstructured meshes. And I kind of got in the game of almost doing mesh generation codes, and it wasn't a whole lot of fun for me, but we ended up wanting to strip this out when started working with the team who's working on a code called Hopper. And it's the higher order preprocessor, but it's essentially a tool that allows you to restructure unstructured meshes and reorder elements so that you can get really nice domain decompositions fairly easily. Essentially, what they do is they reorder elements along space filling curves so that you can minimize the number of MPI communications that are happening. So there was a bit of work to transition everything to be compatible with that kind of file IO to work with Hopper. And then to make things a little bit more user-friendly, we're looking at putting in a command line interface tooling, so where someone can define dictionaries to set parameters for their applications and kind of define those sort of on the fly. So we've done a little bit of work there. And then, of course, the main stuff that we'll be talking about today is the transition from CUDA-Fortran over to HIPFort. And then there are some test models that we've started to put in so we can benchmark how things would perform for end user applications. Where we're at today, these green check marks really indicate what I could say we've completed, in that the code build, the code runs, code gets the right answer for these various things, and it works on a variety of hardware. We have made a good deal of progress in getting the multi-GPU implementation in place. I'm just not quite ready to sign off on it quite yet, but we're getting pretty darn close. So let's talk a little bit about some of the algorithms. And a lot of this is really just to set the stage so you have a feel for the kinds of patterns that that we're working with here, both in terms of memory storage and in terms of the compute stencils that we operate with. So again, generally what we're trying to do is solve a generic conservation law where you have a time-dependent set of prognostic variables that you can predict the state of in the future using the divergence of a conservative flux and then a bunch of non-conservative source terms. And if you pose a problem in this way, it actually can get pretty complicated when you start talking about doing complex geometries. So on the right here, this is just an example of, you know, an unstructured mesh in 2D. But the way we go about solving this problem numerically is to divide a physical domain into what are called elements. Here, they're in 2D, they're quadrilaterals. And in 3D, we use hexahedrals. And within each element, you represent your solution as Lagrange interpolating polynomials. And the nice thing about this kind of structure is it gives you a very obvious way to do your domain decomposition. And it inherently has a lot of really dense computations that are that you can do on memory that's really close together. I guess, you know, of course, at the end of the day, someone can choose to order memory however they want to, but in our case, what we typically do is in Fortran, the first few array dimensions are really dedicated to representing the solution inside a particular element, and then on the outer array dimensions are indexing over elements. Now, the typical polynomial degree size ends up dictating how much memory you have per element, and we typically operate between about polynomial degree 4 to 7. So you have, you know, basically 5 by 5 floats or doubles in 2D, or of course, if you're in 3D, it would be 5 cubed to up to 8 cubed data points per element. Now, when we do this in this problem in physical space, essentially what we do is each element gets mapped to what's called a computational domain. And in the process, we keep track of all these metric terms. So computing a divergence is not as simple as just taking a derivative of a bunch of interpolants. We also have to take into account metric terms in the process. We'll talk about that here in a minute. In terms of the computational patterns, everything comes down to representing the functions that you're trying to model as interpolants. And when you code this up, essentially, you're looking at having discrete nodal values of your function within each element, and then you multiply by your Lagrange interpolant. So at the core level of self, everything rests on a few routines that are basically for working with Lagrange interpolants. So if I wanted to regrid, what we can do is actually break this summation down. If I had a set of knot points for this CI variable, essentially this Lagrange interpolant at point I, evaluated at some Cj, ends up giving you a matrix to interpolate from one point to another. And of course, if you wanted to take a derivative, you end up just taking a derivative of the interpolant. And so from this, I mean, this is really the foundation of what's in place here. So everything comes down to basically doing series after series of matrix vector multiplies. As you go to higher order dimensions, you know, the whole cycle repeats. So all I do is add a sum out front, increase the number of indices I have on my data points in front, and of course, I just do tensor products of the Lagrange interpolating polynomials. So again, we're just doing sequences of matrix vector multiplies over and over to do various operations like derivatives or interpolation. Yeah, so 3D process repeats. So like I said, you know, differentiation comes, it really does come in two flavors for us. So in the strong form, essentially when we take a derivative of a function, we approximate that by the derivative of the interpolant. So again, I can take the derivative of that interpolant, evaluate it at those same knot points, and I get a matrix out front. So when I want to compute a matrix, I essentially do a matrix vector multiply. And again, if I go higher order dimensions, you can see how this process again repeats. And I just stack up the number of matrix vector multiplies I do in order to go to higher dimensions. The weak form is a little bit more challenging. So if you're not familiar with the weak form, essentially what we're trying to do is, it's particularly useful for problems where you might have sharp discontinuities in your solution or your flux variables. So if you're doing things like modeling shock waves, things like that. Essentially what you'll do is you'll weight the derivative operator with the test function and integrate over your element and then apply integration by parts once. So it moves the derivative operation off of the function and onto a test function that you know is smooth, so that you can allow for non-smoothness in your actual function. So when you calculate a derivative in the weak form, you do have some extra work to do, but you get something back in terms of actual numerical stability, which is quite nice. And so you end up having these extra boundary terms that you have to worry about. And so we actually store boundary matrices to do these kinds of processes, in addition to a slightly modified derivative matrix. But in the end, at the end of the day, what you still have is internal element operations are just matrix vector multiplies. And then on the boundaries where you can actually couple information between elements, you just do vector products to calculate derivatives. Now, to make things more complicated, like I said, we're also doing things in mapped coordinates. Now, for 1D, this is not really a problem because mapping in one dimension just comes down to multiplying by a scalar. But once you go to 2D and 3D, you actually have to keep track of those coordinate transformations. And I mean, we could spend hours talking about differential geometry. This stuff is absolutely fun. But at the end of the day, what we essentially do is within each element, we keep track of this coordinate transformation from computational space to physical space. And we calculate things like the Jacobian and these other vectors, which are called the contravariant basis vectors, that tell us the direction of the coordinate system at every point. And if you project your flux vectors onto those contravariant basis vectors, you can then do derivatives in your computational space. So the process ends up being, okay, I can calculate a flux, I can then project it into computational space, and then I can do derivatives just as I was before. Just to give you an idea, I mean, we'll go over the algorithm here in a minute, just to show you how this all kind of comes together to dictate the sort of structure we have to work with in this code, both in terms of memory and in algorithms. Now, the cool thing, just to kind of summarize where we're going here, remember, we're just trying to solve conservation laws in general. When you map your map to another coordinate system, all that happens is those vector overbars become squiggly overbars, and the derivative operator ends up being the divergence operator ends up being a divergence in computational space. But essentially, the structure of the equation is almost unmodified. Now, for most of the cases we've looked at so far, we're primarily doing what are called discontinuous Galerkin methods. So we do look at the weak form of this conservation law. Which ends up being a little bit more complicated. But again, you multiply this equation by a test function, integrate over each element, and what you end up with is internal point-wise evaluation terms, which when I get to the next slide, you'll see how this drops out. We have internal point-wise evaluation points. We have dot product with a derivative operator here. So here's where our matrix vector multiplies end up happening. And then we have a boundary integral, which is really what's done to couple elements together. Now, the cool thing, and this might be a bit much, and I've always debated putting equations in slides, but I have no better way to communicate this stuff. When you discretize this for running on a computer, you go from those continuous integrals to discrete operations. You end up getting the integrals become sums. And so again, those internal operations end up being matrix vector multiplies. And then those boundary terms are just vector products. And it's these F star terms that end up really communicating information between elements. Now, you'll notice right out, maybe not, but I'll point it out here, the summation over n here. So if I were to look at the ratio of the number of operations I need to do term by term here, this term here, if I'm in 3 dimensions, there's n cubed points, but I have to do reductions over n. So there's n to the 4th operations that are happening. And on the boundaries, I only have n squared points, but I'm doing vector products. So I have n cubed operations that are happening for boundary terms. So the ratio of the interior computations that I have to do to sidewall computations, and even the number of communications that I'm doing is order n. So the higher polynomial degree I go, the higher that ratio of work to communications I have. So, in some sense, spectral element methods do offer this ability to not only get you refinement for your solution that's spectrally accurate, they do have some favorable qualities when it comes to keeping the ratio of work to communications as low as you want. So that's really the gist of it there. And of course, the other terms we have to work with, like these source terms, are just pointwise evaluations, so they're all order n cubed as well. And this, of course, if we were just to think about scaling, the number of flops I do for derivative operation versus any of these other terms being larger, it's no surprise that in most cases, this is where most of the work is done, both on CPU and GPU hardware. So let's go ahead and move on to the next slide. So just to summarize, to give you just a reiterate, what the steps are in an algorithm here to solve a conservation law with spectral element methods. Essentially, what we want to do is within each element, we want to prolong the solution to element boundaries. We can do exchanges of information between neighboring elements. So that's where most of our MPI activity happens. And then we calculate internal fluxes and do those contravariant projections. Calculate element boundary fluxes. This is where what we call a Riemann solver would happen. And this is where you do things like implement boundary conditions. Of course, you have element to element interactions as well. And then once you have those two bits of information, you can actually do that matrix vector product over and over, depending on how many spatial dimensions you're in, and calculate your flux divergence. Then you add that to your source terms and use that to feed into a time stepper and kind of repeat that process over and over. So all that being said, this is what leads to the particular software design that we have is, at the bottom end of everything here, it's all based on the idea that I have an interpolant. And I can do tensor products of that interpolant to get me into higher dimensions, 2D, 3D simulations, things like that. And essentially everything we do is element wise. All those internal derivative operations that we are doing can be done independently across each element. The only time we ever couple between elements is when we're doing those side exchanges. So this kind of dictated for us what that memory layout needed to be. And this actually, as I was learning how to do parallel programming since 2014, it was a journey figuring out a lot of this stuff, but this is what we've landed on so far. So for the interior storage of data on these elements, we basically index, and so I'll just do 1D and then walk you through 2D, and the pattern kind of repeats for 3D. But for storing scalars so mathematical scalars, of course not scalars in the programming sense. In 1D, we index over the polynomials nodal points in the first dimension. And then we index over a number of variables because you might have multiple prognostic variables for a problem. And then you index over the elements. So this way, whenever you're doing computations, the data within each element is as close as possible to each other. When you go to 2D, you now have scalars, mathematical vectors, mathematical tensors to work with. So scalars, again, all we do is we keep those polynomial degrees out front, then the variables, then the elements. When you go to vectors and tensors, we actually stick those vector dimensions in the tensor rows and columns out front of the polynomial degree so that at each point, usually the majority of operations that we do are typically working within those, working with those dimensions usually at the same time. And then in 3D, of course, that process repeats. Again, scalars have all their polynomials degrees up front, then the number of variables, then the number of elements. And again, vectors have their direction component first, then the polynomial nodal points, and then the variables, elements, etc. Now the sidewalls are a little bit different when you store sidewall information on an element. So 1D, it's just a point. So you just immediately index over the number of variables, the number of sides, and then the number of elements. And then in 2D, because on a 2D side, it's really an edge. When you're in 2D, you have a 1D polynomial for your sidewalls, variables, and then you have 4 sides to your element, and then of course indexing over the elements. And the same rules apply for the vectors and tensors. And again, we've stuck those directions and the rows and columns out front. 3D, right, process repeats. In 3D, a scalar now on a sidewall is really a 2D plane. So we have a 2D polynomial representation on the sidewalls, etc. And so essentially the whole program is based on the idea of essentially mapping between, information on the internal elements to these sidewalls. You have certain operations that are done to exchange information on sidewalls between elements. And then you have certain operations that operate just on those interior components. Now, in terms of the software hierarchy, this is where it actually really starts to matter for us, because it was, it took a lot of just thinking very, very carefully about how to lay out some of this stuff, because we wanted to run both on CPU and GPU. And once I get into how we do this with HIPFort, I think that this will start to make a little bit more sense. But at the very bottom end, we ended up having to make a class we call self-memory. And it's essentially a bunch of boilerplate code where you can declare various sized multidimensional arrays with an accompanying C pointer. And the reason why we have to do this is because the Fortran pointers at the time we were doing this were not supported in HIPFort. And so we had to have a Fortran pointer for host side code or for host side usage, and then a C pointer for the GPU side usage. But essentially that self memory class is really just used to help us like keep clean allocating and deallocating memory for both host and device, and then give us a clean API for doing host and device memory copies, and of course host device memory deallocation. So once we have a way to describe how data gets onto hardware with the self memory class, we start building up the Lagrange class, which really provides the core routines for interpolation, both within an element, and of course for doing that prolongation to element sides. So that's your grid interpolation and boundary interpolation. And then we have routines for divergence, gradient, curl for 2D and 3D, and then in 1D just derivatives. And you also want to just, typically when we're doing conservation laws, we want to work with mathematical scalars, vectors, and tensors. And if you were to take the cross product of, the types of operations we want to do with the Lagrange class and the type of data we have, this gives you roughly like 48 routines that we wanted to have. And then, of course, we want to implement them on the CPU and GPU. So that's 96 routines out of the box. And of course, we complicate things because we want to do stuff in mapped coordinates. So if you go a little bit higher up, we have a bit more information to add to this. So we have a what we call the self mesh. And this is the component that's really compatible with that Hopper format I mentioned earlier. But essentially, it defines basic connectivity like you would need for any unstructured mesh code. So we have nodes, edges, faces, and elements all represented both on the host and the device within this class. And then because we're doing spectral element methods, we also need to keep track of geometry information within each element. So, we need to know the physical positions and how those map to the computational coordinates. And on top of that, we need to have things, particularly the covariant basis vectors, so the derivatives of those positions with respect to computational coordinates. We need to have contravariant basis vectors, which are calculated from those in like Jacobians, things like that. Now, the cool thing is we can kind of bootstrap ourselves a little bit to get what we call the self-map data class. And the idea being, if I have a Lagrange class and I know I can calculate derivatives in the strong form using that Lagrange class, if I have positions, the physical positions within my elements, I can use that Lagrange class to calculate all those metric terms, and then I can use those two together in addition to the mesh to create this self-mapped data class. And the self-mapped data class, all it really does is it's a type extension of the self data class to account for the extra geometry. So we still have the same divergence, gradient, curl routines, derivative in 1D, except now it incorporates mapping. But the same process repeats. So now we're up to 96 by 2 routines. So 192 routines just out of the box for all those classes. So it's a bit of work to get all this going. And then you have a couple higher, one more level above all that to really tie it together for someone who is a scientist and just wants, they know the conservation law they want to solve, and they really just want to say, here's my prognostic variables, here's the conservative fluxes, here's my Riemann solver, go ahead and integrate. So we have what's called a self DG class. So again, it ties together that map data, the mesh geometry to implement discontinuous Galerkin methods for conservation laws. And there are a handful of methods that are deferred. It's like things that I just can't define until I actually know what that conservation law is, particularly like a Riemann solver, internal flux calculations, etc. We are also working on a continuous Galerkin solver to help folks who are doing elliptic and parabolic systems. And this is pretty common, and I can only speak for the domain that I'm familiar with. But for those who do like Boost-esque equations and they need to couple pressure to momentum equations, typically there's an elliptic solver that needs to be done there. But of course, there's tons of other scenarios where elliptic equations are used. But the general idea is the same. We pull together all these other classes down below, stitch them together to provide a fairly generic interface for doing continuous Galerkin methods in 1D, 2D, and 3D. And then on top of that is where that model would come in, and that's primarily where someone who would use self would sit, is they would basically do a type extension of either self DG or CG, or make their own class on top of some of the other data types that are available to make their own solver. So in the end, this is kind of a bird's eye view of the I wouldn't say a call graph, but some type of dependency tree. So on the far right here, this is just showing the dependency trees for the advection diffusion solvers that we put in as test cases. But again, if you were to follow back through this, you would find that the self-advection, for example, 3D, it's going to depend on that DG class, which depends on that map data, which depends on the geometry and mesh, all the way back down to the Lagrange solver. Now, all this pattern-driven design was done so that I, as a single person developing this code, wouldn't have as much code as I had before. And right now where I'm at is I was able to shave off about 60% of the code that I had before, simply just by following this pattern-driven design, and then kind of keeping things tidy along the way. So there's a heck of a lot of code reuse that went into this, so that I wasn't having just like a lot of bespoke kernels that were written sort of just to solve a specific problem. The main issue I came up against when I was transitioning to HIPFort was the explosion in the number of lines of code, simply because now I'm not just managing Fortran code, I'm managing C++ code, and then there's a lot of other boilerplate interface stuff that needs to come into play. So all this pattern-driven design was meant to do is to make this code a bit more maintainable as I went through this transition over to HIPFort. So let's talk a little bit, now that we got all the basics out of the way, about the memory management. Particularly, we'll look at some comparisons with what I had before, just some example snippets of code, what we were doing with CUDA-Fortran, and how that changed when we went to HIPFort. So if you've coded with CUDA-Fortran before, there's a lot to like about it. One, you can code in Fortran syntax. You didn't have to do mixed language programming. And of course, the downside I think a lot of us saw was, well, I'm vendor locked. I'm stuck with just this one compiler. I'm stuck with just this one GPU. And that was not appealing to a good number of us. Certainly limited who could use our code, and at the end of the day, who your customers could be. Depending on how willing they are to buy into a specific piece of hardware. However, the nice thing that we had when we were doing CUDA-Fortran is this device type for any Fortran basic type that you had. So if you had a real, if you had integers, whatever it was, you could always decorate it with this device specifier, and that would tell the compiler to put that piece of data on the GPU whenever you called an allocate statement. Which was the other nice thing, is I could actually use the same Fortran allocate statements that I had before to allocate that data over on the GPU. It didn't look any different than any of the other data allocations I was doing. And my favorite, which the summer students absolutely loved, they didn't know Fortran when they came in to Los Alamos, and this was just one feature I remember them expressing quite a bit of joy over, was just simply putting an equal sign, because PGI had implemented an operator overload for equals to do mem copies between host and device, which if you write it in C++, you're doing this full API call to hit CUDA mem copy to do that. So of course, comparing between CUDA-Fortran and CUDA-C, this, again, it was just something nice that kept the code nice and tidy, a little bit more maintainable. So with HIPFort, like I said before, we ended up having to implement, or we felt like we needed to implement this self-memory class to handle both host and device data. As before, basically every class that I had for every host attribute, I had a device attribute, but in CUDA-Fortran, I could just decorate with device and be done with it. So what we've actually done is we made these series of derived types in the self-memory module, and we prefix them with HF for HIPFort. And then we have reals, which we've provided a build time variable called press, which you can toggle at build time between double and single precision, We have also defined 16-bit, but I haven't dared try it for for any of the solutions that we do. But the idea is the naming convention is it's HF and then the data type that's underneath the hood. So we also have this for int32s and int64s. And then the number, the rank of the array that you're declaring. So we have R1 through R9. Some of our variables are 9-dimensional rank Fortran arrays, which is kind of weird, but it's needed for some of those tensor arrays, things like that. So in this type, we really just have two attributes. One is that Fortran pointer, which again is meant to just host that. It's meant to store that host side data, so on the CPU. And then we use a type C pointer. So in this module, we do have to use ISOC binding to bring that in. And then each one of these gets a alloc, a free, an update host, update device. And the alloc routine, essentially what it does is it uses some of the HIPFort API calls to check to see if you have a GPU available. If you do, then it allocates space for that device array. And then same thing with those update host, update device. Everything's wrapped in a conditional that says, hey, if GPU available, then do these operations. So that way I can build one binary in the end, and someone can actually make use of this particular class. So here's an example of what that update device looks like. When you're using HIPFort, you have to bring in two modules. So HIPFort, of course. And there's a useful one called HipCheck, which can actually check those exit codes for you and safely exit if you wanted to use it that way. I've been considering for some time putting in some more robust exception handling, but for now, this actually works quite well, and it gives me meaningful output when things go awry. So that update device routine, again, I have, this is all boilerplate code because I basically rinse and repeat this for every data type, every rank array that we have there. So that can get used. But essentially what we do is call this HipCheck wrapped around a HipMem copy call, which returns an integer error code to do a mem copy. In this case, if we're doing update device, the one thing you do have to do is whenever you're referencing that device data, you have to pull out the C location for the Fortran pointer, because the hitmem copy routine expects to have a C pointer. And then of course your device data, it's already a C pointer, so that's already good to go. And so in some sense, it looks very similar to the C API for hitmem copy, for CUDA-mem copy. It's just in Fortran syntax now. The hitch again is that you do have to use these C pointers. Now, there is a recent development as of a couple of months ago. We haven't propagated through self yet. They have added support for Fortran pointers, but for reasons that will become clear here in a few slides, I've been hesitant to do that. But if you were to use the Fortran pointers, it does shorten this up a bit. You don't need the cloc call anymore. And you don't actually end up needing this size of entry when you're doing this mem copy with Fortran pointers on both sides for the host and device pointers. And the reason why is the Fortran pointers also store information about the size of the pointer, or the amount of memory that's held there, and they've implemented some stuff to pull out that information for you. So again, it does help reduce the number of lines of code that you're working with. Now, the nice thing is at the end of the day, once you get through all this boilerplate code, independent of what rank array you're using or what data type, folks can just use a call that looks like this: update device or update host, alloc or free. It's very straightforward, very consistent across the board. All right, so let's look at GPU kernel implementation and some comparisons with CUDA-Fortran. So again, another nice feature of CUDA-Fortran that was really attractive was the ability to write your CUDA kernels in the Fortran syntax. So again, the PGI compilers were able to expose this global attribute. Let's see if I get a laser pointer on here. This global attribute, which, if you're writing in CUDA C or HIP C, you end up having to declare all your kernels with this global attribute, which merely decorates the subroutine to say, hey, this is something that can be called from the CPU, but it's going to execute on the GPU. And then again, you could still use those device decorators on all your variables. And it was just really nice not have to work in multiple languages. So when I go to do this in HIPFort, you know, at the end of the day, I would like something clean to use so where I can just call, you know, in this case, vector DG divergence, and I can pass in the variables that are needed. And it would, and ideally, it would decide underneath the hood how to run. Would it go on the CPU? Would it go on the GPU? And what we wanted to have was, you know, if F, BF, and DF were uh, Fortran pointers, then it would run on the host. If they're C pointers, then they'd run on the GPU. So there's a few key ingredients to make that happen. So these top two end up replacing what we had as the CUDA-Fortran kernel, the thing we originally wrote in Fortran to run on the GPU. So we actually had to write HIP kernels in C++, and you also have to write a C++ wrapper that goes around that, so that you can expose that wrapper routine into Fortran, set up an interface so you can end up calling that kernel from the Fortran side. So this is really the part that replaces the CUDA-Fortran kernel. So now you're this again, like I said, you're doing mixed language programming at this point. It's really not too bad. And then of course to meet this, I would say self-specific requirement of being able to have one clean interface and just toggle between running on CPU and GPU based on the data type that's sent. We end up putting in Fortran wrappers around those, and then doing generic type bound procedures so that the compiler can make those decisions at build time. So I'll kind of walk through what each of those look like to give you a feel for how this is implemented. And of course, Self is completely open source. And at any time you can check that out. So the HIP kernel, you know, if you've written CUDA before, it's identical to CUDA. You know, the AMD team has done a really good job at making that easy. So if you're already in the realm where you were one of the folks who were doing Fortran plus CUDA C and did not go the CUDA-Fortran route, you're in luck because most of that work's already done. But yeah, essentially, you know, we would write a C kernel with the global decorator out front, and you can use those block IDX, thread IDX intrinsics like you had with CUDA to pull out, you know, the thread variable, the thread IDs that you're working with, so you can determine what each thread's going to do in that kernel. A really important thing to point out is that on this wrapper, the thing that actually launches that kernel is you want to wrap that in this extern C decorator. And essentially what this does, it tells the compiler not to mangle the routine name. What I mean by name mangling is what'll happen in this object files and the symbols. What the compiler will do if you don't have this decorator is it'll throw this name together with usually a few of the arguments that are in there. So when you go to call it from Fortran, you might think you're trying to call vector DG divergence 3D GPU wrapper, but the code will complain it doesn't know what the heck you're talking about. So wrapping it in the extern C, make sure that like this name here that I have out front is the name that's in the symbol. That's the symbol name that can be called from the Fortran side. And so long as, like, if you're really careful, you don't have to do anything beyond this. In the Fortran side, you can literally just call this routine and just put an underscore at the end. That's what the C compiler does, is it inserts an underscore at the very end of this thing, and you could call that from the Fortran side. Now, I like to be a bit more verbose, so I know what is external to my Fortran code. And so I prefer to put these interfaces in place, but if you were really careful, you could get away with not putting this extra, I would call it boilerplate code to make this all happen. But on the Fortran side, what I do is we'll define an interface block within each module. And in that interface block, you set up a subroutine, and you know, for consistency, I keep those names on the Fortran side the same as the ones on the C side. And then, of course, we're using ISOC binding, so you can bind that to a C routine, and you give it that same name that we had on the C code. And again, we have to use ISOC binding so we can declare everything as a C pointer, so that Fortran knows what those data types are. So that's ingredient number 2. So we've got our GPU kernel that's actually going to be doing the GPU compute. Got the wrapper in C++ that is going to launch that. And now we've got an interface in Fortran so that we can now do basically a subroutine call in Fortran syntax to launch it. So, and again, this Fortran wrapper part is really specific to self because we did want to have a generic interface that made it look seamless to the developer on the other side, depending on whether they sent a device variable or a C pointer or a Fortran pointer to allow it to toggle through. But essentially, we put together a Fortran wrapper where its only job is really to call that GPU wrapper in the C++ code. So it takes in the C pointer data and launches that, calls the C wrapper, which then launches the GPU kernel. And the last bit there to really tie it all together was a generic interface, so that now I have vector DG divergence 3D is the name of the routine someone can call up. And then, of course, depending on whether they give a C pointer or a Fortran pointer, it dictates whether it's going to call the CPU side kernel or the GPU kernel. And so, basically for every routine we have these generic public block, a procedure private declaration, just so we make sure we only expose this, and so folks don't have to think about whether they're running on the CPU or GPU. So again, it was a bit more code than we originally had, but from a lot of the changes in the software design, we were able to keep the number of lines of code fairly manageable, so it wasn't getting too unwieldy. So looks like we're doing good on time. Let's talk a little bit about domain decomposition and MPI. So, all right, I hope, and yeah, feel free to ask questions along the way. So on the domain decomposition, all of our domain decomposition happens over the element, so we never divide an element across two processes. And like I said at the beginning, I spent a lot of time working with things like Metis and integrating that into Self to like reorder all my elements and get things laid out nicely so that I can get well-balanced MPI implementation, and of course minimize the number of MPI communications I'm doing, which was becoming a code of its own, and it was just such a chore to work with for me. But there are some really talented people in the high order methods communities, and I'm so glad that they took a stab at solving this problem. And so I've really stripped out a lot of that mesh generation and mesh reordering stuff from Self, and just said, I'm going to start relying on some tools that are out there, particularly Hoke Mesh. It's the high order hex quad mesher. This is one from David Capriva, and then Hopper, which is part of the Flexi frameworks. They have Trixie framework doing Hoke Mesh, and then Flexi doing Hopper. But the idea behind Hopper particularly is it can digest a lot of standard unstructured mesh formats that are out there, convert low order meshes into higher order meshes, and then also do some element reordering for you, so that basically I can just do 1D domain decomposition over my elements. And if I were just to chunk over the elements uniformly across each of my ranks and in order, because they reorder along space filling curves, it ends up giving me a fairly reasonable domain decomposition. It's not always fantastic, but I would say it's very robust in terms of getting very, very decent domain decompositions out. So that's really just the idea behind how we do this. Is all our domain decomposition is just over that last dimension of all those arrays. And the nice thing again is that most of our work is done inter-element, and it can be done process independent. So in our experience with Self fluids before the refactoring, we actually did get pretty decent scaling, up to, I think we were only looking up to like 32 GPUs at the time. But it was doing fairly good. And I'm pretty excited to see what this ends up looking like for us down the road. There's a couple of gotchas when you're working with C pointers in Fortran. Of course, if you have a C pointer and you want to do device to device communications, which I'll be honest with you, setting that up as a system administrator is it's a challenge to get the MPI stuff built correctly. And then, of course, some of the operating system kernels built correctly to do device-to-device communications. But if you have that all set up and you wanted to do device direct or GPU direct communications like we had with CUDA, if you're using those C pointers, this is I guess one of the downsides of using C pointers is you actually have to call CF pointer, which is from the ISOC binding module, to convert your C pointers to Fortran pointers so that they can actually be digested by the MPI interface in Fortran. Of course, it was, you know, it's a silly thing. I assumed when I first implemented it, I was like, oh, I'll just throw the C pointers in there. And of course, the first thing that comes back during build is you can't send a C pointer through this Fortran interface. What are you trying to do? But the general pattern for doing MPI communications now is in each one of those mapped data classes that we have. So again, those vectors, scalars, tensors, 1D, 2D, 3D. We essentially had this kind of pattern where at the very top, we'll do a call to CF pointer to get that C pointer over to a Fortran pointer. And then we actually do our send and receives off of those rather than the C pointers. And again, that's only for the device-to-device communication, the GPU direct communications, which, because I'm not certain that every system I'm going to be running on is going to have that set up properly, we do have an option in place for doing, you know, what we used to do before GPU direct was a thing, which is essentially copying the device pointers over to the host, doing your MPI exchanges on the host side, and then copying back when you're done. That latter method is not super great for scaling. And so it is really critical that, you know, if you have a system, make sure that they have GPU direct set up, because AMD GPUs do support it. And of course, if you're working with the C pointers, this is a bit of a chore. If you do opt to go with the Fortran pointers, which are now supported in Fortran, a lot of this stuff is moot, so you don't have to worry about it. Again, I've got my particulars about how I want the API to be set up, and that might be a little bit of a pitfall for me, but this is how I end up working around it in this particular case. So again, yeah, if I'm using those Fortran pointers, all that stuff goes away, and then I can just send device data as is if I'm just using that Fortran pointer. All right, so I'll talk a little bit about the single GPU benchmarks and that we have currently. We're still working on getting some correctness issues worked out on the multi-GPU side, but we're getting pretty darn close. So I wasn't quite comfortable sharing that stuff quite yet, but I'll show you where we're at so far and how we're getting some of our results. So we run everything primarily on the cloud at Fluid Numerics. We have one node in-house that has an MI25 GPU on it, but most of our compute's done on a system we designed called the Research Computing Cloud. It's hosted on Google Cloud. For the cluster we're looking at, I'll be showing some results on V100 GPUs and A100s. The host operating system has CentOS 7, CUDA-11.5, and ROCm 4.3. Everything we build, we essentially ship out Singularity containers that have self pre-installed. When we ran this, we were looking at Singularity 3.7, GCC 9.3, and we actually had CUDA 11.4 inside of that initially. I had to actually do a separate install of CUDA on our cluster to get that stuff to work, but the ROCm versions did match. We did get some time on the AMD Accelerator Cloud, thanks to some folks over at AMD. We did some testing on the MI50s and MI100s. And on their side, they were looking at Ubuntu 20.04 and ROCm 4.3. So there's two sets of benchmarks I'm going to show you. One is a repeat of some stuff that I had shared earlier in the year, where we're just looking at the DG divergence kernels. So really just the in 3D, those matrix vector multiplies plus those boundary terms. So yeah, if you remember the algorithm, right, we do boundary interpolation, Riemann solver, contravariant projection, and that DG divergence. And what we're primarily looking at is those last two components. I'll preface all of this with saying no specific tuning was done for a particular GPU. We basically had those memory layouts that I showed you before, and essentially the way we do the grid and block arrangement for launching on the GPU side is, when you're doing internal element operations, basically the polynomial degrees end up forming your blocks, your GPU blocks, and then the grid is just basically indexing over the variables and elements. So it sort of naturally maps to the way the CUDA or HIP API wants you to launch your kernels. So what we're looking at here is on the y-axis is the duration per call for that DG divergence kernel, and on the x-axis is basically we're increasing the mesh size. In all these cases, we're looking at polynomial degree 7. So again, those grid sizes are 8 by 8 by 8, the block sizes are 8 by 8 by 8, and then we just increase the number of elements to increase the problem size. And the different colored bars represent different GPUs and different precision levels. So starting from the top down, we've got the MI50s with 64-bit, MI100 64-bit, V100 64-bit. So those are our more expensive GPUs. These are ordered in terms of decreasing compute time. And then we've got the MI50, MI100, V100, all 32-bit as the next three. So if you were to look at any one of these, that's pretty much the order you end up seeing. Is out of the box, the Nvidia GPUs do a bit better. And we're currently working through a lot of events profiling to figure out what specific optimizations are needed to really tweak performance on each particular hardware. But this is our first cut from back in June, looking at those vector DG divergence kernels. The more recent stuff we've been doing is building out these more fully fledged models. So what I'll show you next is the advection diffusion solvers, both in 2D and 3D, and give you some comparison of how we do against CPUs and, of course, the various GPU hardware. So in the advection diffusion 2D, so we're looking at a problem with basically 25 elements. And you could think about just taking a square domain and dividing it into 5 by 5 elements. And then within each element, we have 7 by 7 degree polynomials. So again, this is the 8 by 8 block pattern. The first three large bars that are very noticeable are what the runtimes are for 10,000 time steps on the CPU for Intel Cascade Lake, Intel Broadwell, and then actually our MI25 node here has an AMD Ryzen 5 in it, so it's a consumer grade chip. Now down below are the GPU runtimes. Again, no special optimizations for any particular hardware. We've got the MI25 coming in about 3 seconds, followed by the Nvidia A100 and then the V100 running the fastest there. In general, the CPU to GPU comparison holds in the 3D case. It's actually a little bit better in the 3D case, and it's particularly because our CPU code is actually not too great for the 3D. Since most of our focus was on developing the GPU code, we weren't surprised to see basically in the order of 100x over serial CPU performance. Which, of course, if you do ideal scaling, this puts us in, the realm of like 10 to 14x over a fully subscribed, 16-core chip. Again, the MI25 performance difference between the NVIDIA chips ends up really starting to shine a little bit more here for the 3D problem, simply because there's more work to do. But what was really peculiar to me was when we look at a hotspot profile for that advection diffusion 3D solver, the relative importance of the various steps in the algorithm. So at the very, very top on the MI25, which is what's shown on the left, the three most expensive routines in order are the contravariant weight. So the basically projecting from the physical space to computational space. And what we actually have is a tensor divergence, which is done for calculating gradients. There's when you're doing mapped geometry, doing a gradient in 3D ends up becoming a divergence operation with a tensor. Anywho, so yeah, on the MI25 we have the contravariant weight, then the tensor DG divergence, and then a contravariant weight actually applied on the boundary of the sidewall. So I was pretty surprised to see that show up in the top three for the MI25. But then again, I actually end up seeing the contravariant weight on the boundary show up on the right side on the V100s as well. The difference between the V100 and the MI25, though, is that the V100 had behavior that we had seen before, where the actual doing the divergence operation, in this case, the tensor divergence, was the most expensive, and then it was followed by the contravariant weight. So, of course, we should expect, because it's different hardware, there should be different optimization strategies. This kind of seals the deal for me to say, okay, well, if I'm getting different sort of like fingerprints for my hotspot profiles, I should expect to have to do different things to get my code to run efficiently on an Nvidia GPU than I would for an AMD GPU. And the challenge there is, again, getting on this code maintainability side is now I'm looking at having to do C pre-processing flags to pull out what target GPU I'm looking at, and doing various tunings based off of those CPP flags. So at the moment where we're at, again, it's stuff that we have up in the air and we're still trying to understand what's going on. So wasn't terribly comfortable presenting on that information. But what we're doing at the moment is looking at events profiling for the MI25 V100s, the MI50s, MI100s, and the MI250s as well, for these top 3 routines, to understand what the heck's going on, to see what we can do to bring down that runtime on the AMD GPUs. And of course, at the same time, because we want to cater to folks who have whatever GPU, we're looking at the same process on the Nvidia side as well. As I think it's going to be a very educational exercise to understand what it takes to get the best possible performance across multiple hardware. And since we do have a little bit of time, I want to just share something that's pretty exciting to me, because basically what I want to be able to do at the end of this stuff here is we now have a fairly large suite of tests that we run to make sure the code that we're putting in the repository is actually working properly, is automating a lot of these tests, and of course automating a lot of the benchmarking that we're doing and hotspot profiling, so we can keep track of whether or not changes we're making are causing problems or heading in the right direction. So I'll talk a little bit about the continuous integration and continuous benchmarking, some of the portability testing infrastructure that we're trying to put together, so we can do this. And of course, because we're a very small business, to do this in a cost-effective manner. So when we build the code, and I think a lot of groups do this, I would certainly not say I'm alone in this one. We want to do quality assurance and quality control to make sure that what we end up delivering in those singularity containers works. And the questions that come to mind for me are, does it build? Does it run? Does it get the right answer? And of course, this last one, does it perform well? And because we want to serve a wide range of users that might be doing work on a laptop or a workstation or a supercomputer or a small, research cluster, we need to make sure that those questions are answered positively for serial CPU builds, parallel CPU builds, single GPU and multi-GPU builds. So already answering these questions with these 4 constraints ends up being, a lot of testing to do. In fact, you have at the very least 16 by however many tests you want to run. And then, of course, you want to top this off with the variety of platforms that are available for each of those builds. So I might have, something that's targeting Intel x86 versus AMD x86. I didn't put ARM on here because we haven't been doing that quite yet, but at some point this will likely be an area where we want to look into. And then, of course, on the GPU side, we have AMD GPUs, Nvidia GPUs, and on the horizon for us is looking at the Intel Xe GPUs as well. I'm still looking for support for those through HIP, but I suspect that'll be coming hopefully in the near future. So basically, once if we want to answer these questions every time we make a commit to the code, we have these 4 types of build. We have these various platforms we want to hit, and of course, from each vendor, there's multiple GPU types that we want to have. So the number of tests we have to do is it grows pretty quickly just from the combinatorics here. Sorry about that. My dog's barking. I'm sure we're all used to that now, though. So like I said before, we primarily operate on the cloud, and we're starting to address this issue of kind of answering these questions when we make commits. And I guess the only problem we have now is because we're able to do a lot of these builds automatically and run some of these tests automatically is keeping those costs under control. So we're trying to figure out ways to dial back on the number of tests we do. But essentially the idea is, since we run on GCPs, we use a GitHub repository for self. And whenever we push commits to that, it kicks off through what's called Cloud Build to run a tool that we made called Fluid Run. What Fluid Run does, it essentially spins up ephemeral compute resources with GPUs attached to execute the code. So the build trigger will create the singularity containers targeting the various GPUs we want to target. And then Fluid Run digests a YAML dictionary and takes care of scheduling stuff through Slurm, which is on this compute network here. And it runs on various GPUs, the V100s, A100s, and I think we go back to even the P100s still. What we're currently working on is doing a federation to our on-premise node, this AMD MI25 instance, so that we can still connect via this Fluid Run instance to this controller to schedule with a Slurm controller we have on premise to get those runs to actually go on AMD GPUs. So we can at least verify correctness on AMD hardware. Ideally we'd be running on something like an MI100 or something more modern, but at the very least, this starts to answer some of the questions for us that we want to have answered. Now, when the tests are actually done executing, of course, we publish singularity containers to a bucket that folks can grab those containers from. And then we also collect from the Slurm job scheduler all the runtime information, how much memory was used. And part of our testing, we include calls to MVProf to output hotspot profiles into CSVs that can all get dumped into a what's called a BigQuery database. At the end of the day, that information that ends up in that BigQuery database, if jobs fail, we get exit code information. We can hit standard out, standard error, so we can diagnose from a single panel what went wrong. But the nice thing for us too is we can actually start to make nice panels that tell us, okay, here's the hardware you ran on, here's the various commands that you ran, and here's the runtimes for those, so we can at least keep track of how performance changes over time. So I'm glad I had enough time to sneak that in, because that's pretty exciting for me to be able to start to make it a little bit easier for me just to sit down and code and push things off and kind of plug back in when I need to without having to get really invested in doing a lot of runs on a static cluster. So as I mentioned, Self is available online. It's open source. Anyone who wants to grab it, contribute, work with me on it. This has been a project of love for years, and I look forward to finding ways to keep working on it somehow. Yeah, you can find that at GitHub under Fluid Numerics Self, and every week on Fridays at 4 p.m. Mountain Time, so that's early in the morning for the folks over in Perth. I do live coding sessions as I'm working through Self, but when I am done with those, I do go through and annotate them, so you can basically quickly skip through on YouTube to various spots where I'm doing specific activities, like, hey, I'm writing the GPU kernel. Hey, I'm writing a wrapper. I'm doing, whatever the activity was. So you can kind of easily find out examples on various coding strategies for working with GPUs. We do have planned for next year a number of tutorials for working with Self to build conservation law solvers. Of course, in the process, we're building out compressible Navier Stokes and a Maxwell's equation solver. So we'll be definitely streaming those. And then, of course, there's tons of documentation we got coming out that has a lot of the stuff I talked about today in terms of the software layout, in the hopes that other people can see an example of how we did it. And we can, share ideas with the rest of the community. So I know I ended a little bit early, but I'm open to any kind of discussion you guys have on our experience. And I hope I touched on things you guys found useful.